Got about 1 minute left technically, so I'm going to go ahead and start. We are covering chapter 11. We finished chapter 10 last time. I did, enough examples. I feel there's also, of course, more examples on my YouTube channel, as well as the ones that I've actually put in the module for this week and for last week and stuff like that. So you can find all sorts of lectures. Uh, you might want to look up like Atwood machine, stuff like that. But I'm getting ready to work now at chapter 11, and we're starting off with the idea of Newton's second law for rotational motion, which is, if you remember Newton's second law, how it was originally stated, even though we didn't cover that initially, we initially covered F equals ma, or I like to write it as the summation of the forces is equal to m times a. That works. You just have to remember that A is technically a second order derivative of position with respect to time, unless you're lucky enough to have a mass and a total force that's constant, in which case you end up getting A is just a constant, so you can just solve for it. Uh, but that was the original version of Newton's second law, according to the way we used it. But the actual, real initial version that Newton gave us was F, the summation of the forces, is equal to dp dt, the instantaneous rate of change of momentum with respect to time. The rotational analog to that is the summation of the torques is equal to dl dt. And we can also make the equivalent analogy for the one that's F equals ma. That would be the summation of the torques is equal to I times alpha. So that's the two versions that we're using. I've already talked about them ad nauseum in chapter 10, but like I said, I am going to go ahead and start by sharing the screen and start working the examples in chapter 11. So this should open up in a second. So now we have that open. And what I want to start off with is a pretty straightforward example, example 11.1. I'm hoping that you might have done this before. You can take and tie like a pencil or something fairly light and not necessarily dangerous. Like I tried to excite my kids today, my students today, by doing it with a pair of scissors, uh, which were heavy and steel. And if I did that and the string broke, it would really be an injury. In fact, I hit myself in the head twice, so that wasn't quite as cool as I'd hoped. But anyways, if you imagine, let's say this is not a string, this is a bread tie type thing, but either way, if you imagined it was a string and you were holding it like this, if you had a mass tied to the end, you could swing it over your head and things would go pretty well. But the neat thing is, if you pull down like this, then the radius of the circle that that mass is spinning around is gets smaller and smaller, and conservation of angular momentum is going to dictate that the moment of inertia, which is decreased because the radius went down, that decrease in moment of inertia is going to cause a equal increase in the angular velocity omega. So it literally speeds up. And if you do it too hard or with too heavy an object, the string will literally break. And of course, if that was scissors or a dagger of some sort, we'd obviously get hurt. So that's what this problem is to start with regarding example 11.1. So example 11.1 says object rotating on a string of changing length. And the problem says a small mass M attached to the end of a string revolves in a circle on a frictionless tabletop. The other end of the string passes through a hole in the table, figure 11.3. Initially, the mass revolves with a speed v1 equals 2.4 meters per second in a circle of radius r1 equals 0.80 meters. The string is then pulled slowly through the hole so that the radius is reduced to r2 equals 0.48 meters. What is the speed v2 of the mass now? So, as I said, this is example 11.1. And just to give you a sort of picture of what's going on here, I'm going to imagine that here's the tabletop, and I'm drawing it in perspective. That's why it's tilted on the sides here. There's going to be a little hole here. And what we're going to do is right now, we're imagining the scenario where the mass is going in a circle of radius R1. And then we're going to pull that in so that the mass then goes in a circle of radius r2. Radius r1 is going to be associated with a velocity v1 equals 2.4 meters per second, and radius r2 is going to be associated with a velocity v2 equals question mark. I'm going to go ahead and say that r1 is 0.80 meters and r2 is 0.48 meters. And of course, I've already written that v1 is equal to 2.4 meters per second. But the argument behind why this works and why the equation is what I told you it was is that Newton's second law says the summation of the torques acting on the system is dl dt, where torque is defined to be r cross f if you're talking about at least a single object, and L is defined to be r cross P, again, if you're talking about a single object, and that is, of course, R cross M times V. So that's what those quantities are. Now, in this case, if you treat the system as the string and mass, then other than maybe a slight bit of friction that might happen from the cord going down into the hole or the friction that the object has on the table, other than that, there's no forces on the system from outside of the system, and the book explicitly tells you to assume a frictionless tabletop. So we can get rid of that. That means there's no forces acting on the system except for forces that are part of the system. Now, I'm going to imagine, for instance, when I do this, that the string was pulled this way out the bottom. And that is technically a force, but it's a force, not a torque, because the force is actually going to pull the string, and the string is going to cause the object to move into a shorter radius. But that velocity or uh, that force is actually acting with no lever arm, so it can't have an actual torque. It's literally just pulling it into the hole, so it doesn't introduce a torque. And since the summation of the torques is equal to zero, therefore dl dt is equal to zero, and that means L, the vector, is equal to a constant. It's a constant vector, but it's still a constant. And that is the very definition of conservation of angular momentum. Remember, this is the type of question that you're expected to be able to answer at any test now that you've had chapters 1 through 11. I could ask you, what's Newton's first law? What's Newton's second law? What's Newton's third law? What's Newton's law of gravity? What's Kepler's first law? What's Kepler's second law? What's Kepler's third law? I could also ask you, under what conditions is momentum, linear momentum, conserved, and under what conditions is angular momentum conserved? That's me taking the time to explain to you under what conditions angular momentum is conserved. So make sure you're paying attention to that. Now, in addition to L equals R cross P, L can also be written in many cases as L is equal to I times omega. And your book states that, but it happens to be one area where this fifth edition of the textbook has a typo, and it says L minus IW instead of L equals IW. So just pay attention to that. So in this case, what we're going to have is, since the L is a constant, that means L initial is equal to L final. And all of this motion is going around on the tabletop. And according to the right hand rule, that means your angular momentum points perpendicular to it. And we can handle that just by pluses and minuses. And we don't have to worry about any extra components. So it's basically a scalar equation at this point. Even though the thing that we're dealing with is perpendicular to the plane, we don't even have to think about that. So in this case, it becomes I initial omega initial is equal to I final omega final. But we also know that V is equal to R times omega. So omega can be written as V over R. With that in mind, we then can say I initial V initial over R initial is equal to I final times V final over R final, like that. Now, in this case, we actually have a point object, a mass M that's out some distance from the center, and all of its mass is acting as if it's concentrated at a distance r. So that's just like a hoop. Therefore, the moment of inertia is mr squared. So with this case, I'm going to say m times r1 squared times v1 over r1 is equal to m times r2 squared times v2 over r2. And you can see that the r2 in the bottom cancels out the exponent in the top. The same thing with the r1 and the exponent in the top there. And this mass m cancels out on both sides. So we can finally get that v2 is equal to r1 over r2 times v1, and that is equal to 0.80 meters divided by 0.48 meters times 2.4 meters per second. So when I do that math, I get zero point 0.8 divided by 0.48. That gives me 1.6666. Now I'm going to multiply that by 2.4, and we really only have two sig figs to work with. This works out to be 4.00 meters per second. And that's how we work a typical, really easy, quote unquote, conservation of angular momentum problem. Anybody have any questions on that one? So notice I did.
Um,
Go ahead. Go ahead, Kyler.
you used L a lot. Does L just stand for angular momentum?
Yeah, L is the symbol we use for angular momentum. I don't know why we have it, but at least there's an L in the word angular. So
Maybe it's
unlike
just
the
because
P in
L
momentum.
is itself an angle.
Yeah, maybe that's it. uh, but yeah, that's a weird one, as is P for momentum. I don't know why that's in there either. So, anyways, anybody have any other questions on that? Okay, so we're going to go to example 11 too, which is another nice one, and it actually teaches you a little bit about stuff. So, for instance, not everybody necessarily knows what a clutch is, and we're not talking about a clutch like a lady's bag or anything. This is a clutch like you'd find in a car. So, of course, this one is clearly not a car because it turns out to have a diameter of 1.2 meters, and I don't know any regular cars that have a transmission that's 1.2 meters in diameter. Well, it's actually got to be literally bigger than 1.2 meters. So I don't know anything like that. But here's the problem. It's example 11.2, and it says clutch. A simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. The two plates have masses MA equals 6.0 kilograms and MB equals 9.0 kilograms with equal radii. R0 equals 0.60 meters. They are initially separated. Figure 11.4. Plate MA is accelerated from rest to an angular velocity of omega 1 equals 7.2 radians per second and a time of delta t equals 2.0 seconds. Calculate, A, the angular momentum of MA, and B, the torque required to have accelerated MA from rest to omega 1, and then finally C, next, plate MB, initially at rest but free to rotate without friction, is placed in firm contact with the freely rotating plate MA, and the two plates then both rotate at a constant angular velocity omega 2, which is considerably less than omega 1. Excuse me, which is considerably less than omega 1. Why does this happen and what is omega 2? So I'm going to go ahead and write down what we're given. We were given that MA is equal to 6.0 kilograms. We're given that MB is equal to 9.0 kilograms. Everything's in two sig figs, in other words. we're given that the two radii RA equals RB equals R0 is 0.60 meters. We're also giving that omega 1, well, I should say omega initial is equal to 0, but omega 1 is equal to 7.2 radians per second after delta t equals 2.0 seconds. In part A, we want to know the angular momentum, so L sub A, and I'll put an I on there just to point out that it's initial. So what is that? Part B, we want to know the summation of the torques. In other words, what total torque could bring that up to that speed. And then finally, part C, we want to know omega 2 equals question mark. So I'll just draw kind of quickly the figure that we're talking about here. So for starters, you can look at it as if we have a plate on a rod like that. Uh, of course, this is supposed to be the rod connected to it, and that means this ends here and that ends there. So you can see that it's actually that. This is MA, by the way, and it's rotating. And what's going to happen is we're going to have a similar disk. Oh, that one's not it. We're going to have a similar disk that has a mass MB. Whoa. And its initial velocity is 0, but we're going to move it up like that. And when they touch together, believe it or not, you don't need teeth or anything to grip the two plates. The friction alone is enough, especially if you apply it with a little pressure. And that's, of course, why you feel if you ever drive a vehicle with a clutch, you'll feel a little force fighting you on that. But the main thing is that pressure against it causes a connection that is frictionful and sufficient to actually cause the rear wheels to rotate without actual teeth or anything like that. So let's start off with part A. We want to calculate the angular momentum. This is essentially, we can ignore the little axle because what we're really thinking about is we're imagining that little axle holding MA. We're imagining that as if it's really light compared to the actual mass of the disk. So we're going to go with just the disk part, in which case the angular momentum initial, LA, sub I is going to be the mass, or excuse me, the moment of inertia of the disk times the angular speed of the disk. That moment of inertia for a cylinder is 1/2 ma times r0 squared. And then that angular velocity is just omega 1. So now I'm going to put in all these numbers. I'm going to say 1/2, and remember that's just from the derivation I did deriving the formula for the moment of inertia of a cylinder. The MA is 6.0. I'm going to leave off the units here. I will explain to you what the answer units are, but I'm going to leave them off just to save some space. The R0 is 0.60, and that's going to be squared. And then the angular velocity we found would be 7.2 radians per second. So that is the entire quantity LA initial. So when I go to calculate that, we're going to see it's zero point 0.5 times 6 times zero point 0.6 times zero point 0.6 times 7.2. That gives me 7.776 radians, or excuse me, the units here turn out to be a kilogram for the mass, a meter squared for the r squared, so that's kilogram meter squared, And then a radian, which isn't truly a unit, it's just a pure number, so we can leave that off. So we're going to get kilogram meter squared per second. Another way of saying that is a Newton is kilogram meter per second squared. A Newton meter is a kilogram meter squared per second squared. So this is clearly a joule second because a Newton times a meter is a joule. So we're going to call this a joule second, but you could also call it kilograms meters squared just per second, which is also equal to 7.776 joules times seconds. We're going to learn later if you actually get to quantum mechanics or if you just happen to do some quantum mechanics homework for extra credit, you're going to find that the joule second is the unit that they use for angular or for Planck's constant. So that's why sometimes we end up using joule seconds for conservation of, or excuse me, for the units of angular momentum. Anybody have any questions on that? Of course, that rounds to 7.8 to the appropriate sig figs. Now, for part B, we want to find the torque, and what we know is the summation of the torques is equal to I times alpha. So I've got to figure out what alpha is, and we can then just multiply that by I, and that'll give us the total torque. The I, of course, is 1 half m sub a r0 squared, and then the alpha is what we're looking for. So the alpha is equal to omega, in this case, I called it omega 1 minus omega 0, or omega I is what I called it. And all that will be divided by delta t. So this is going to be 7.2 radians per second minus 0 over 2.0 seconds. And we're going to get the summation of the torques is therefore equal to 1 half times 6.0, leaving the units off again, times 0.60 squared times, in this case, 7.2 divided by 2.0 would be 3.6. So that's times 3.6. And that has units of radians per second per second. So if I multiply all this, I get zero point 0.5 times 6 times zero point 0.6 times zero point 0.6 times 3.6. And that's two sig figs across the board. That's going to be equal to 3.89. And you can tell these units work out to be basically kilograms, meters squared, per second squared, which of course is a Newton meter. So we're just going to call that a Newton times a meter like that. And that's the torque required to make that thing accelerate at that rate. And I covered up my line showing that that wasn't a sig fig, so I had to redraw it. Anybody have any questions on that? All right, now we have to use conservation of angular momentum to figure out part C, and we do that as follows. So here's part C, and what we have is the initial angular momentum, LA sub I, is equal to the final angular momentum. And that initial angular momentum, of course, we already figured out that was 7.776 joule seconds. The final angular momentum is going to be the sum of the two moments of inertia because they're both stuck together and rotating about the same axis and rotating, since they're stuck together, rotating at the same angular speed. So this is going to be 1 half MAR0 squared plus 1 half MBR0 squared. That's the moment of inertia. And the angular speed, which is what we're looking for, is omega 2. So in this case, what we can do is calculate the moments of inertia. And in doing so, I'm going to get zero point 0.5 times 6 times zero point 0.6 times zero point 0.6. That gives me 1.08 for the first moment of inertia. 0.5 times 9 times zero point 0.6 times zero point 0.6. That gives me Crap. Zero point 0.5 times 9 times zero point 0.6 times zero point 0.6. That gives me 1.62. I don't remember getting that answer before. And all of that times omega 2. Anybody verify that you got 1.08 and 1.62 for those two moments of inertia? It looks like everything I did was right, but I don't remember getting 1.62 before. All right, so all this means that omega 2 is actually equal to 7.776 joule seconds divided by 1.08 plus 1.62 gives me 2.70, and that's kilograms meters squared. Remember, a joule second is a kilogram meters squared per second. So, with that in mind, you're basically just going to get units of reciprocal seconds, which can be written as radians per second. And in so doing, I'm going to say 7.776 divided by 2.7 gives me 2.88, and that's in radians per second is equal to omega 2. So that's how you solve yet another conservation of angular momentum problem. Anybody have any questions on that one?
Wouldn't it be 2.78?
Not what I got. No.
I got
Oh, I'm
2.88
sorry, I
as well.
divided by 2.8, not 2.7. My
Ah,
bad.
yeah, that would do it. Good deal. But thank you for checking on it, and it's good. I mean, it doesn't harm us when you accidentally make a mistake, because obviously that helps me too, because I obviously make mistakes. So please keep up doing that. I appreciate it. Anybody have any other questions? Now, one of the more drastic effects that can occur is happens in astronomy, or specifically just in outer space. It turns out that as the star goes through its life processes, unless the star is really small mass, like the factor of 10 smaller in mass than our sun, in those cases, in those small mass stars, there's actually an active circulation that takes the hydrogen and helium that's in the star and it mixes in and out of the core constantly while it's living, as best we can tell. So you actually get access to virtually all the hydrogen in a really low mass star. But the vast majority of stars, which actually I shouldn't say that, it turns out that stars that are lighter turn out to last so long that really the low mass stars are way more prevalent than the high mass stars, strictly speaking, because the high mass stars live much shorter lives. But, anyways, if you're dealing with a star roughly the size of the sun, it's pretty much going to run hydrogen by fusing hydrogen into helium. And the mass of the four hydrogens that go in is slightly less than the mass, or excuse me, slightly more than the mass of the four, or excuse me, of the four particles that make up the helium nucleus, two protons and two neutrons. And almost all of that difference in mass multiplied by c squared is the energy that comes out from each of those fusion reactions. I say almost because it's actually creating some other particles like a positron, an anti electron, in other words, and some neutrinos, which, as best we can tell, are massless. But the main thing is the rest of it's just pure energy. Now, when that star starts to run out of hydrogen, since it doesn't have a circulation mechanism, it's going to just run out of hydrogen in the core, and then gravity is going to force that thing to squish the core. The core is going to get smaller, and because it got squished, its temperature is going to go up. And if the temperature goes up enough, it can go to hot, hopefully hot enough where hydrogen isn't the only thing that's available to fuse now. Now helium can fuse, but helium, it turns out hydrogen takes about 10 million Kelvin, whereas helium takes about 100 million Kelvin to fuse. And if it squishes and reaches that 100 million Kelvin, then the hydrogen can start to fuse into carbon and other elements as well. When that happens, it causes the whole thing to shrink, and that happens again. You run out of helium to fuel the carbon fusion, and then you start running into another type of fusion where another element, and it goes through silicon and all that stuff. ultimately, the death knell is when the fusion produces iron. It turns out that there's no energetically favorable fusion or fission that can happen from iron. It turns out if you fuse from iron into something else, then that takes more energy put in to get it to fuse than you get out. And the same thing if it goes the other way by fission. So the iron's always going to be a death knell. What ultimately happens is the core becomes an iron core, and then the gravitational forces try to close down again once it stops having all the radiation pressure pushing out, and it ultimately can become either a white dwarf, which is basically a bunch of carbon atoms, mostly a bunch of carbon atoms, or it can go further where the force is so huge that it overcomes the Pauli exclusion principle force, the force that makes electrons not allowed to occupy the same quantum numbers. It can overcome that, in which case it's forcing the electrons into the nucleus, and the electrons basically form with the protons into more neutrons, and you end up having what's called a neutron star. It's almost essentially a big pile of neutrons packed with the density of a nucleus. So you can imagine, for instance, a single teaspoon of that would weigh as much as a cruise liner or a cruise ship, basically. So that's what's happening here in this example 11.3. So let me do that one for you real quick. Example 11-3. This is on a neutron star. It says astronomers detect stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form from the inner core of a massive star that collapsed under its own gravitation to a star of very small radius and very high density. Before collapse, suppose the core of of such a massive star is the size of our sun. The radius is about 7 times 10 to the fifth kilometers, with mass 2.0 times as great as the sun, and is rotating at a frequency of one revolution every 100 days. That's a typical star rotation rate. But the other thing about stars is when they rotate what we call differentially, so that the equator goes a little faster than the poles do. So it's not like a rigid body. But anyways, if it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would its rotation frequency be? So this is a case where obviously the net external torque acting on the system is zero, so angular momentum is conserved. What we know is R1 is equal to 7 times 10 to the fifth kilometers. Now, normally you'd think, okay, we need to convert that kilometers to meters, and you normally do, but in this case, you're going to see that everything sort of multiplies and divides out in such a way that you can keep it in kilometers. So I'm going to do that, and you'll see it happen. R2 is going to be actually just 10 kilometers, like that. And we're seeing the mass, which isn't going to change, by the way. The mass of the star, which I'll just put M star, is supposed to be 2 times the solar mass, and the symbol for solar mass is a circle with a dot in the middle, for obvious reasons. Okay. Now, with that in mind, we also have to realize that the rotational rate or the frequency, really, it's more of a frequency because it's talking about cycles or revolutions per minute or per time or per second or something like that. But the really only difference between omega and f is a factor of 2 pi. Omega is actually equal to 2 pi f. So it's okay for us to use f. And in this case, it's one revolution per 100 days, and I'm going to keep that. Okay, we will remember that omega is 2 pi f. So when I say L1 is equal to L2, that means I times 2 pi f1 is equal to I2 times 2 pi f2. So you can see that the 2 pi's just cancel out. We're not going to need that at all. And now we can go ahead and work it. For stars, they're generally spherical, and the moment of inertia for a sphere, which you can find in a table, or you can derive your own self, and it turns out to be 2/5 mr squared. So I'm going to say 2/5 times 2 times the solar mass times R2 squared. That's the moment of inertia. Okay. And then that's going to be multiplied by just plain F1, which is 1 revolution per 100 days. That's the initial. The final will be 2/5. It's still going to be the same 2 times the solar mass, but now it's going to be R2 squared. And now we're going to find a new angular frequency, F2. So what you can see right now is the 2/5 will cancel out with the 2/5. The two solar masses will cancel out with the two solar masses. And what we're going to get instead is that F2 is going to equal. Ooh, I wrote R2 on this left-hand side. I don't know why I did that. I guess because I was thinking ahead, but that's R1. So make sure y'all make that change. And I'm going to go ahead and put parentheses around this frequency 1. So this is going to be R1 over R2. Those quantities are squared, and that's going to be times 1 revolution per 100 days. So this turns out to be 7 times 10 to the 5th over just plain 10. And notice it's kilometers over kilometers, and those two are canceling out. That's why I didn't really need to convert them to meters, because whatever conversion factor I'd use in the top is going to cancel out with the conversion factor I'd use in the bottom. I just do have to remember to square it though. And I'm going to treat this as 1 revolution per 100 days. So I'm not even going to change the 100 days. I'm just going to leave it as some number of revolutions per 100 days. And when I do that, I get 7 times 10 to the 5th. Whoa, I did all sorts of stuff wrong there. So 7 times 10 to the 5th divided by 10 is obviously going to be 7 times 10 to the 4th. And now I'm going to square that. And that gives me 4.9 times 10 to the 9th times 10 to the 9th revolutions per 100 days. So that's the new frequency, but that's not necessarily in units that are that helpful. So I'm going to go ahead and convert it to units that are more helpful. So we're talking 4.9 billion revolutions every 100 days. Oops. I wrote the revolutions without the times 10 to the 9th. Per 100 days. So I can go ahead and make that 4.9 times 10 to the 7th revolutions per 1 day, like that. And then all I have to do is say, well, 1 day is equal to 24 hours, and 1 hour is equal to 3,600 seconds. So that'll give me revolutions per second. So divide the 4.9 times 10 to the 9th by 100. That gave me 4.9 times 10 to the 7th. Now I'm going to divide that by 24. And now I'm going to divide that by 3,600. And that gives me 567 revolutions per second. So it went from 1 revolution every 100 days to basically about 600 revolutions per second. And that's the answer your book got. Just because they were only using 1 sig fig, they said roughly 600 revolutions per second. I should fix that. I wrote that right through the middle of my number 7, and that wasn't very kosher of me. So I'm going to go weep. Looks perfect. Anybody have any questions on that? Okay, so there's another example, example 11.4, and this is a typical one that I want you to be able to solve as well. So I want to work with something like this. What I'm showing you here is some very specific conservation of angular momentum type problems that I expect you guys to be able to solve. There's a lot of other ones, and I certainly, expect you to solve the homework problems and to work the practice test problems. But when I go to test you, it's going to be more like these things that you're seeing, these specific examples. That's what I'm leaning towards. So let me go ahead and do example 11.4. Let me change my program again because it's making me angry. 11.4. It says running on a circular platform. Suppose a 60 kilogram person stands at the edge of a 6.0 meter diameter circular platform, which is mounted on frictionless bearings and has a moment of inertia of 1,800 kilograms times a meter squared. The platform is at rest initially, but when the person begins running at a speed of 4.2 meters per second with respect to the Earth around its edge, the platform begins to rotate in the opposite direction, as in figure 11.5. Calculate the angular velocity of the platform. So, in this case, you see very distinctly a human is running on a circular disc like a merry-go-round. Clearly that human is applying forces at some distance from the rotation axis. So clearly that human is putting a torque on the disk. So if you wanted to solve for how fast that disk is going, if you just use the disk as the system, then you'd have to know something about the force that the runner is actually applying to the disk. But in this case, we're not given any of that information. We don't necessarily know what that information is, so we can't do it that way. But what we can do is we can assume that the system is the person plus the disk. And then when the person first got on the disk, he wasn't moving or anything, so the total angular momentum was zero. That means after he starts running, the total angular momentum will still have to be zero because there's no external torques. The only place torque would come in here is the air resistance that would tend to slow down the merry-go-round or the runner, and also the friction that would tend to slow down the disc. But they're saying this is frictionless, and we always ignore air resistance just about. Okay, so I'm going to draw a diagram that looks roughly like this. This distance is 6.0 meters. That's the diameter. The radius, of course, is 3.0 meters. And then out here on this edge is the person. And this person weighs 60.0 kilograms. I'm going to call that mass little m. This disc, on the other hand, has a moment of inertia equal to 1,800 kilograms meters squared. And the person is going to run at V equals 4.2 meters per second. And the disk, of course, is going to rotate the opposite way, and we want to know what that angular speed is. I think I have all the information. 60 kilograms, 6 meter. Yeah, we're good to go. So, again, the summation of the torques is equal to zero. Therefore, dl dt is equal to zero. Therefore, L is equal to a constant, which is a constant vector, of course, and that means angular momentum is conserved. What we know is L initial is equal to zero, and we also know that L is equal to I times omega, because both of these are, in some sense, revolving around an axis that is common to them. If the guy running was running around a different axis or had a different angular momentum other than parallel to the one that it had, then I omega wouldn't work, but in this case it does. So the final angular momentum, LF, is going to be the moment of inertia of the disk. So that's I disk times omega plus the moment of inertia of the person, so IP times omega p. Okay. Now, what we do know is the person's running at the end, so V is equal to R omega tells us omega is just V over R. Now, additionally, the person is probably pretty small compared to the disk, so we can treat him like a point object. And in that sense, we're going to think of him as a mass m at a distance r away. And it's the only mass, so the moment of inertia in that case is just mr squared. So what we now have is 0 is equal to the moment of inertia of the disk, which is 1800. I'm going to leave the units off for the same reasons we've been talking about. The omega of the disk is just going to be plain omega, and that's what we're looking for. The moment of inertia for the person is going to be 60.0 kilograms times the radius, which is 3.0 meters squared, so that's mr squared, times the angular speed, which is the velocity divided by r. So in this case, I'm going to say 4.2. I said I'm going to keep off the unit, so I don't need that there. And then that's going to be 4.2 divided by 3.0 meters as well. You can see that this 3.0 is going to cancel out with that exponent of 2. And now we can see that omega will be equal to the negative of the 6 times 3 times 4.2, or excuse me, 6D times 3 times 4.2 gives me 756. And that is actually the whole angular momentum. So that's joule seconds. And that's one extra sig fig, by the way. That's one extra digit other than a sig fig. And now I have to divide that by 1800. I'm going to put the units back in, kilograms, meters squared right there. So you can see that it literally comes out in radians per second and specifically negative. So now I'm going to take 756 and I'm going to divide it by 1800. And that gives me negative 0.420 radians per second is the final velocity of the disk, the rotational velocity, anyways. If you wanted to know the velocity of the end of the edge of the merry-go-round, then you just multiply that 0.42 times 3 meters, and you'd get 1.26. So 1.26 meters per second would be the velocity at the end point. Anybody have any questions on that one? All right. So the next example is a conceptual example, and I want to explain that to you. And this is one where I'd much rather do a demonstration, but let me look on here real quick, see if I can find something. Kevin Mitchell's YouTube. That's my friend and coworker. I was figuring he's probably got a couple that he's made on here, but I do not see them now. Nope, still that, not that, not that. Okay. Let's see if there's any here. Not there, not there. Ah, here's one. So what I'm going to do real quick is I'm going to stop sharing and then I'm going to start sharing with this. So let's do share, and I'm going to share my screen, and it's that screen right there. And here's Dr. Wright on my friend Kevin Mitchell's page.
Sir,
Yes.
we can't hear anything.
You aren't hearing that? I was turning it up.
No, it's
Okay.
completely mute.
All right, let's kill this for just a second. The main thing here isn't the noise, what I want you to see is he just got that wheel started, so I'm going to narrate it for you. Don't worry about what he's saying. In fact, I'm going to go ahead and kill the volume. So, what's going on here is he's going to start this wheel rolling, and he's on a seat, he's on a chair that actually has the ability to rotate. So he's first going to get the wheel started. Now this wheel's made a little better, so it actually has quite a bit of weight on the end where the tire is. They often would literally fill the tire with lead shot, but you can see he's actually making that rotate in a counterclockwise direction as seen from above, and that's the way he's holding it. And he turns it over, and notice when he turned it over, it actually made the chair rotate in the opposite direction that he was rotating. Then when he brought it back to counterclockwise again, then that made the chair try to turn the other way. So that's the demonstration that we're trying to do, and that is also what this conceptual example is trying to show you. So in this conceptual example, they're saying, okay, we have a wheel spinning this way. Okay, notice if you looked from above, that would be counterclockwise. So it goes to the right when it's closest to the, or to your right when it's closest to the screen, and so on and so forth. Now, that means, according to our right hand rule, my fingers curling around this way tells me the angular momentum of that wheel is up, and he's sitting in a chair with the angular momentum up, and that's all the angular momentum it has. The friction forces and all that are pretty negligible, so we're going to assume that angular momentum is conserved. And what he's going to do is take and turn that wheel upside down. If he turns that wheel upside down, then all of a sudden the wheel is rotating this way, which is clockwise, and then you see the L vector would have to point down by the right hand rule. But conservation of momentum dictates that the net angular momentum must be up. So what's going to have to happen is, in order to compensate for that wheel now having an angular momentum that was exactly as big as it was before, but now it's pointing in the opposite direction, is it's going to have to create another angular momentum twice as large pointing in the other direction. The first one is just going to cancel that one out and give us zero, but that's not what we want. So we then need a second one so that it'll give us back the original angular momentum up. Well, since that has to be up, you turned the wheel, which was rotating counterclockwise, you turned it now to clockwise, and now the actual person in the chair is going to have to rotate counterclockwise with twice the angular momentum. As luck would have it, Dr. Wright weighs quite a bit more than that tire, and that chair combined with him weighs even more. So he doesn't have to spin nearly as fast as the tire does to actually get the same angular momentum. But the main thing is it went the opposite way. And as you saw, when he tried to flip it back the other way, it reversed again. So hopefully that was helpful to you. Anybody have any questions on that one? All right. So that was conceptual example 11.5. And now I'm going to go ahead and share my screen again for my iPad. And we'll continue on. Okay, so we're back here. Whoa, don't know what happened. Uh-oh. There it is. I want the share there. It did something weird that time it wasn't supposed to do. Ah, there it is. It went straight to my iMac, so it wasn't showing my Zoom window. That was the problem. And I have no idea why the sound didn't come through on that last one, but anyways, no big deal. So we've done conceptual example 11.5, and your book then does the vector cross product, which I already covered in chapter 10, and we've covered it pretty well. But that being said, I'd still like to give you an example of calculating a cross product. And I'm specifically going to use example, it says 11.6. So I'm going to go with example 11.6. I'm going to start it on the next page. Let's say example 11-6. What they're giving us is that there is a vector r that we sort of treat as our lever arm. There's a vector r that has a x component that's equal to 1.2 meters and therefore points in the I hat direction, plus a y component that's also 1.2 meters, and that points in the j hat direction. So that's our lever arm vector. And we're saying at the point of the tip of that vector, this vector runs from the rotation axis along the object that's being rotated to the point of application of the force. And at the end of that vector, there is a force given by 150 newtons in the I hat direction. So what we know is torque is equal to R cross F, and what we're asked to calculate is the torque. Now, the R cross F is actually a determinant of a matrix. That's the way we're teaching you to do it. And that matrix is made up of the first row being an I hat vector, then a j hat vector, and then a k hat vector. The second row is the first vector in the cross product, so that'd be 1.2, and these were, oh, I wrote that wrong. Notice the second component was not in the j hat direction. It was actually in the K hat direction, so I'm glad I caught that now. Luckily, I remembered working it earlier. And the F is acting in the I, so that's okay. All right, so 1.2 is there. There's 0 in the Y direction, but there's 1.2 in the K direction as well. And now the force is the third row, and the force only has a component in the X direction, so I'm going to put the 150 right there. Notice I left the units off. All right. So what we do is we expand upon each of these unit vectors. So there's one, and there's one. And I told you that the way this works is there's a -1 raised to a power, and the -1's actually in parentheses. And the power that the -1 is raised to is the row number and column number of the entry that you're expanding upon. So I'm expanding upon I hat, and that's the first row and first column. So that number is 1 plus 1, for 1 being the first row plus 1 being the first column. And of course, -1 in parentheses raised to the 2 power is -1 times -1, which is +1. So the I is a +1. So I just do the normal determinant of the remaining matrix. The J, on the other hand, that's the first row, second column. 1 plus 2 is 3, and -1 to the 3 power is negative. So I usually put a negative there just to remind me. But really, what I do to implement it is I do my determinant of my 2 by 2 matrix backwards. And then when we get to the K, that's the first row, third column. 1 plus 3 is 4, and -1 to the fourth power, in parentheses, of course, is positive as well. So I don't have to do that. Now, here's how I go about doing it. I say equals, and since I'm first expanding upon the I hat, then what I do is I imagine the I hat, since I'm expanding upon that, I've already counted the first column and I've already counted the first row. So all I'm left with is this little matrix down here. And the way you take a determinant for a 2 by 2 matrix is this times this minus this times this. That's what I'm going to do. So I'm going to go 0 times 0 minus 1.2 times 0. So I write that 0 times 0 minus 1.2 times 0, and that just gives me 0. Now I'm going to do J, but remember, J is the one that has that -1. So to account for that -1, I'm going to do my determinant backwards. Instead of multiplying from top left to bottom right minus top right to bottom left, I'm going to do it the opposite way. In this case, what we're looking at is expanding upon J, so that gets rid of this column and this row, this column and this row. So all I have left is these two numbers and these two numbers to make a matrix. So my 2 by 2 matrix is these two without the zeros in there. And normally the determinant would be this times this, but I'm going to do it backwards. So I'm going to do this times this minus this times this. So when I do this one, I'm going to say 1.2 times 150. That's this times this. Now I'm going to do minus 1.2 times 0. So that is minus 1.2 times 0. And I'm finished with J. Now I'm going to do the K term. And again, when I do the K term, that means this column disappears and this row disappears, and I'm left with this 2 by 2 matrix. And it's positive, so I just do the normal determinant, this minus this. So in this case, I get 1.2 times 0 minus 0 times 150. And that's it. So the answer in this case turns out to be 0 I hat and 0 K hat. But when I multiply 1.2 times 50, zero point 0.2 times 50 is 15 times 2, which is 30. So this is going to be 180 Newton meters in the J hat direction. And that's equal to the torque. Anybody have any questions on that? You don't have to technically do that, but what I've discovered is, and yes, I give you the formula like the book does. It gives you a formula for the components of the cross product. It specifically says AYBZ minus AZBY in parentheses I hat plus parentheses AZBX minus AXBZ parentheses J hat plus parentheses AXBY minus AYBX parentheses K hat. That formula works and you can do that, but I've seen time and time again, and I've tried to do it myself during a test. It's very easy to get confused which is the X, which is the Y, which is the vector A, which is the vector B, and all that. So the better you are at just computing this, like I just pointed out, the better you are at not making a mistake. So I highly recommend you do it like I just showed you guys. If you want to look for another way, I've done a ton of videos, and many of them are linked in my modules in our course. So by all means, look those up. Uh, we've done that, and that answer, by the way, does agree with the book's answer. Now, what I have is they go into a section on angular momentum of a particle, and he explains a lot of things and does a lot of derivations. Uh, it's not that critical that we necessarily, well, it's critical for you to understand all that. It's just not that critical to do examples on it. So there is one example where it asks you to calculate a particle's angular momentum, but we've been doing that the whole time. So I'm not really sure the need for that conceptual example 11.7. But just for the record, I'll go ahead and do it. So let's say example 11.7. In this case, they say, what is the angular momentum of a particle of mass m moving with a speed v in a circle of radius r? So we've got m, we've got v, and we've got r, and it's in a circle like this. Okay, something like that. And what I want you to understand is they're asking specifically what is the angular momentum. So L is equal to question mark. Now L, oh, let's write it another way. L is equal to R cross P, which equals R cross MV, like this. So if we imagine this thing going around in a circle, and they said it's going counterclockwise, so that means the velocity back here is this way, and then out in front it's to the right, so on and so forth. So this distance right here is R. Tangential to that circle right there is a velocity v. Oops. is a velocity v, and its mass is m. Okay, this vector r, when we cross that with P, remember a cross product takes two vectors and spits out a third vector that's perpendicular to both. So if we imagine the R vector and the V vector being in the XY plane, then R hat, which points outward, or R vector, excuse me, which points outward, crossed with V vector, using my fingers like this, suggests that the angular momentum vector will point perpendicular to that. And in fact, what we'll have is an angular momentum vector, L, that points up that way. Well, what is the magnitude of it? Well, you can see, even though it's not easy to tell here, but you can see since it's a circle and that r is a radial line and that velocity is tangential to the circle, that means that r and v are perpendicular. And we know that the magnitude of a cross product, magnitude of A cross B, is equal to the magnitude of A times the magnitude of B times the sine of the angle between them when they're tail to tail. So A, B, tail to tail, that is the angle theta. Now, if I did A cross B, in this case, it would actually point down, but if I did B cross A, it would point up. So that's what the A cross B is, like that. So if they want to know the angular momentum for this particular particle going in a circle, all I have to do now is go ahead and use the formula and recognize the direction and all that good stuff. So the angular momentum, calling it a vector quantity, is going to have a magnitude of r times m times v times the sine of 90 degrees, which is just 1. And specifically, if I assume this is my x-axis and this back here is my y-axis, then this up here is my z-axis, and the angular momentum vector would just point in the k-hat direction. Okay? You could actually take the time to make out a r vector, make out a v vector, and make out a m times v vector, and then do the cross product, but you'd still get the same results. The other thing you might want to do is realize that it's also I times omega, and if you plugged in v equals r omega, you would see that it would become L equals r times m times r omega in the k-hat direction, but that is m r squared times omega in the k-hat direction. And this is exactly what I told you was the moment of inertia for a point particle going in a circle of radius r. So now we have yet another version as well. So we can say L is I omega as in a vector quantity, but we can also say it's R cross P as well. Any questions on that? All right, so there's a couple examples that would be worthwhile for me to cover. I want you guys to realize that your author does a really good job in section 11.4 and section 11.3 and section 11.5. He's one of the few authors that takes the time to show you exactly what goes on when you balance a tire. So, for instance, if you go to a car dealership or a tire store and you want to replace your tires, they're going to charge you for the tires. They're going to charge you for mounting them, for putting them on the rims, for putting the rims with the tires on them on the car, and then also for alignment of the vehicle, usually alignment for the front and rear of the vehicle. But ideally, it's also going to include a cost for the balancing of the tires. And this is the only author that does anything that helps you understand exactly how that balancing process goes. So even though it doesn't have that many examples in section 11.3, 11.4, and 11.5, you really, really, really should read it so you'd understand these concepts a lot better. Now, with that in mind, I want to work a Atwood machine problem, which is like example 11.8. But I want you to know that even though I'm not doing this other example, which I think is 11.9, it's where a bullet is shot into the edge of a disc. Yeah, 11:12 is what it is. If I don't get to that, I still want you guys to make sure y'all follow that one and learn how to do that one. But I might have time, so I'm going to go ahead and do this Atwood machine that's like example 11.8. So here we go. Example 11.8. So what I have here is a pulley. Okay, that pulley has a very specific radius, which I'm just going to call big R. Your book's calling it R0, but I don't like putting subscripts on stuff unless I absolutely have to. So I'm going to call it big R. I'm going to say that the pulley, instead of telling you the pulley's cylindrical and has a radius R and a mass M, I'm just going to say the pulley has a moment of inertia I. So it has a moment of inertia I. And then I have a mass hanging from it on this side. And I'm using slightly different symbols. I'm going to use a capital M for this side. And I'm going to use a lowercase m for this side. So now this is our Atwood machine, like this. And the way I've got it drawn, it looks as if the left mass is going to tend to rotate the pulley in a counterclockwise direction and lift the lowercase m up. And I'm going to stick with that direction being positive in terms of the y direction being down on the left and being up on the right, as well as positive in terms of rotation when the pulley rotates counterclockwise. So what I want to know in this problem is what is the acceleration? And in this case, you're going to find out that there's a difference in tension on the left-hand side, which I'm asking for, and the right-hand side, which I'm also asking for. I know I'll have time to solve for the A. I'm not sure I'll have time to solve for the TL and TR, so I've been making that as an extra credit problem for you guys to turn in. First, I got to start with the free body diagram. So I'm going to say that on the left-hand side, this is my positive y-axis pointing down because that's the big M and that looks like it's going the right direction. So what I'm going to do with this case is I'm going to say this is a mass big M and it has a force acting on it, and that force is big M times G. It also has another force acting on it, and that force is what I call tension on the left-hand side, so that'd be T sub L. Newton's second law for this tells us that mg minus TL is equal to ma, and I'm going to call that equation 1. Now I'm going to draw, in a consistent way, I'm going to draw a free body diagram for the little mass. Now, in this case, I've got to draw it where up is the positive direction, because that's this, when the little mass is going up on the right, that's the same as the big mass going down on the left, and I want those to be exactly equal. Otherwise, I have to put random negative signs and stuff, and I just don't want to do that. So in this case, we have a force pointing up that is T right. And the reason why the TL and TR are different is if you think about the TL, its job when I pull down on the mass big M, the tension in that rope has got to rotate that pulley that has some mass, plus it's got to lift the rope up on the other side that's pulling the mass little m up. Whereas if you look at the tension on the right hand side, its only job is to lift the mass little m up. So that's why you see they're clearly different. It's because the pulley actually has a mass and potentially could even have friction. In this case, we get a force in the downward direction or the negative direction, and that force is lowercase m times g. Therefore, for this one, we get TR minus lowercase mg is equal to lowercase ma, and that's equation 2, and I'm going to underline that as well. Now I'm going to do the free body diagram for the pulley, and I was really wanting my program to make that a circle, but it did not do that. There it goes. Okay, so we know this distance is just plain capital R, and we know that's actually perpendicular to the string. So in this case, we're going to say TR is pointing in the negative direction. In other words, it's pointing in the direction that we consider a negative rotation. So that's the TR that way. And then on the other side, we have a force pulling in the quote unquote positive direction, and that's the TL. Now, with that in mind, I take the summation of the torques is equal to I times alpha, and for that, that gives me TL times R minus TR times R is equal to I times alpha, and that's equation 3. Now, if we assume the rope is not going to get slack and it's not going to stretch and it's not going to slip over the pulley, then if I pull this rope 1 inch down, the pulley is going to twist so that 1 inch of its circumference moved. And if I did that in 1 second, then it would happen in 1 second. So the velocity of the little masses is the same as the tangential velocity of the pulley, is the same as the velocity of the other mass. Additionally, if I pulled it 1 inch in 1 second and then 2 inches in the next second, then the mass, the big M, would do that, and the pulley would do the exact same thing, and the little mass would do the same thing. So we also have that A is equal to R times alpha, and that's equation 4. So I'm going to make use of that as well. What I'm going to do now is solve 1 for TL, solve 2 for TR, and solve 4 for alpha, and plug them, into equation 3. So TR, which I'm calling this equation 2 prime, TR is going to be M times G plus A. 1 prime is going to be TL is equal to M times G minus A. And 4 prime is going to be alpha is equal to A over R. That's 4 prime. So now I'm going to plug all that stuff into equation 3. And what I'm going to get is M times G minus A times R minus little m times G minus A. Oops. Yeah, I think I'm doing the right one. It was TL was the first one, so that was G minus A with the big M. Yeah, and this would be little m G plus A times big R is equal to just the plain moment of inertia of the cylinder or of the pulley times alpha, which is now becomes A over r. If I divide both sides by r, then I get mg minus ma minus mg minus ma. Remember, I have to distribute that negative, is equal to I alpha, or excuse me, IA over r squared. Now I want to get all of the a's on one side and everything else on the other. So I'm going to write m minus m times g. That takes care of this one, and that takes care of this one. I'm going to pull this one to this side, and I'm going to pull this one to this side. So that's going to become m plus m plus, notice all of them have a factor of a. So I'm going to go ahead and say I over r squared here. And all that is times a. So now I can solve for a, and I see that a is m minus m over m plus I over r squared, all of that times g. And notice I've written it where it has a dimensionless quantity, the part in parentheses, multiplied by a dimension-full quantity that has exactly the units that we want, namely the g. Now, all you have to do is plug a into 2 prime and a into 1 prime to get TL and TR, so I'm going to leave that as extra credit. Don't forget to make sure you do that other example. I think it was 11, 12, but make sure you do that and find TL and TR for extra credit. So that'll just be another homework assignment where you'll get a hundred for it if you do it right. And really all it takes is plugging this A into expression 2 prime and plugging this A into expression 1 prime, and then try to, get a common denominator and get it as succinct or as small as possible. You guys are free to go. Thanks for coming. Make sure you chat me your first and last names if you haven't already. And I will see you all next week. Remember, we only meet on Monday of next week because classes are canceled Wednesday, Thursday, and Friday. I'm shooting for the last face-to-face test will happen the week after Thanksgiving, and the following week will be the week during which you have to do the final exam. So they're literally back to back. We've now finished chapter 11 as well. So have a good one, everybody.
This looks fun plugging in A for TL and TR.
Yeah, it can be a little bit nasty, but once you get the hang of getting a common denominator, it's not so bad.
Um, what's the last unit for this course? Like
Uh,
which chapter?
we're doing 14 and 15.
Okay, got it.
Yeah, that'll be the last. But I went ahead and put 12 and 13 homeworks up as well as 36. All of those are, even though the 36 isn't marked as extra credit, all of those are extra credit that you can just do to help your score, but not necessary. And if you're interested, for instance, in relativity, it might be worthwhile for you doing it. But if it's not, then don't worry about it.
Okay, cool. Thank you.
All right, have a
Good
good
night.
one, Zach. And that looks like it. Bye, everyone.